Hello students, today I am going to explain you one numerical on bar analysis from the unit number 3 for the subject computer aided engineering. So first we will check the contents of the unit number 3 as per Savitribai Phule Pune University syllabus. Title of the unit is 1D finite element analysis. The consistent unit system, introduction to approaches used in the finite element analysis such as direct approach and energy approach. Mostly derivations are asked on this direct approach and energy approach. Next is bar and truss element. So on this particular section only numericals appear in the end semester examination. So which consists of element stiffness matrix, assembling stiffness equation, load vector, stress and reaction forces calculations. Third section is temperature effect on the bar element. So for the bar element, the numericals are asked with the thermal effect. So calculation due to uniform temperature change, stress and reaction force calculations. So today I am going to explain you one numerical. So we will go through that numerical. So determine the nodal displacement of step bar. Okay, as shown in the figure. The bar is fixed at the left end and at the free end a force of F3 is applied. And also a force of F2 is applied towards the fixed end at a distance of 50 mm from the fixed end. So F2 is given as 10 kN, F3 is given as 5 kN. Modulus of elasticity for the first portion of the bar is 200 GPa. For the second portion, modulus of elasticity is 70 GPa. Then cross-sectional area of the first portion is 150 mm square and cross-sectional area of the second portion is 100 mm square. So the free body diagram for the given numerical is a fixed end is there and total number of nodes are 1, 2, 3. 3 nodes are there and 2 elements are there. Okay. So element number 1 and element number 2. Element number 1 is connected by the end nodes 1, 2 and element number 2 is connected by the end nodes 2, 3. So U1, U2, U3 are the displacements at node number 1, 2, 3. So the element stiffness matrix for the first element is A1 E1 upon L1 inside the matrix 1 minus 1 minus 1 1. Okay. This formula have been derived on the basis of the Young's modulus formula E, which is equal to stress upon strain. So by modifying this formula, you got the formula for the element stiffness matrix. So by putting the values, you get the final answer as 10 raised to the power 5 inside the matrix 6 minus 6 minus 6 6. So here on the top of this matrix 1 and 2 is written and on the right hand side 1 and 2 is written. So this 1 and 2 represents the end node of the element number 1. For element 2, K2 is equal to A2 E2 upon L2 inside the matrix 1 minus 1 minus 1 1. So by entering the values for A2 E2 and L2, you get the final answer as 10 raised to the power 5 1.4 minus 1.4 minus 1.4 1.4. And this 2 3 represents the end nodes 2 3 for the element number 2. So these notations of the nodes, node number 1 2 and 2 3 will help you at the time of adding the matrices. So the global stiffness matrix is the assembly of all the element stiffness matrix. So global stiffness matrix K is equal to K1 plus K2. So by writing these two matrices, so here the order of the matrix is going to be so total number of nodes are 3, and there are 3 degree of freedom. So order of the global stiffness matrix is going to be 3 by 3. So now here I will explain you how the first element of the global stiffness matrix is calculated. So 10 raised to the 5 is common. So this 6. So this represents the column number 1, row number 1. So you have to, column number 1 is 6, and here there is no column number 1 and row number 1. So that is why 6 is written. Say for example, I will explain this 7.4. So this represents the column number 2 and row number 2. So column number 2, row number 2 is 6, and here in this case column number 2, row number 2 is 1.4. So 6 plus 1.4 is 7.4. So in the same way, rest of the elements of the global stiffness matrix are calculated. Now the global equilibrium equation is Ku is equal to F. So this is the global stiffness matrix. This is the displacement vector with the U1, U2, U3 are the displacement at node number 1, 2, 3 respectively, equal to force vectors F1, which is at the fixed end, so that is why 0. Force F2 is given as minus 10 into 10 raised to the power 3, and F3 is given as 5 into 10 raised to the power 3. So by applying the boundary conditions in the sense node 1 is fixed, so eliminating row number 1 and column number 1 from the above equation, so which is highlighted with the gray color here, we will eliminate these rows. You get the simplified equation as 10 raised to the power 5 inside the matrix 7.4 minus 1.4 minus 1.4 1.4 U2 U3 minus 10 equal to force minus 10 raised to the power 4 5 into 10 raised to the power 3. So here you will get two equations, 7.4 into 10 raised to the power 5 U2 minus 1.4 U3 equal to minus 10 raised to the power 4, first equation. Second equation, 1 minus 1.4 into 10 raised to the power 5 U2 plus 1.4 U3 equal to 5 into 10 raised to the power 3. By solving these two equations simultaneously, you will get the value of U2 and U3 as minus 8.33 into 10 raised to the power minus 3 mm, and U2 is equal to 0.02738 mm. Thank you very much.